let me introduce the next speaker, our speaker, Prabhjot Singh. Sorry if I misspell your name. His team, uh, weak separation conditions, coincides, finite type condition. Dear Mr. Singh, you're welcome.
So thank you for this opportunity. I guess everybody can listen me.
Here you are, Mr. Singh.
Good afternoon to the organizers and the participants of this conference. The topic of my talk is weak separation condition coincides finite type condition. Before explaining definitions, I would like to make you all familiar with fractal geometry, which is the study of fractals. So what are fractals? Fractals are infinitely complex patterns that are self-similar across different scales. A famous mathematician, Mandelbrot, is called the father of fractal geometry. His book, The Fractal Geometry of Nature, published in 1982, explains a lot of concepts about fractal structure. I assume that many of you are familiar with the Mandelbrot set, f of z is equals to z squared plus c in the complex plane, whose graphical representation I will show you in the last. Mathematically, fractals are the sets for which house of dimension is strictly greater than the topological dimension. So, in general, fractals are broadly classified into strictly self-similar sets and statistically self-similar sets. Examples of strictly self-similar sets are Cantor set, Coates curve, Sierpinski's triangle. And the example of statistically self-similar set is the Weierstrass function, which is written as such. All these examples which are written can be simply found using the Google. Okay, so now let us talk about iterated function systems. Iterated function systems are a method of constructing fractals. It is a finite set of contraction maps on a complete metric space. So it is a unified way of defining strictly self-similar sets. This leads to a simple way of finding the dimensions of the set. When I mention about the dimension of the sets, I generally imply house of dimensions, but also we can talk about the similarity dimension as well as the box dimensions of a set. Now let us see how the construction maps are defined. Let D be a closed subset of our Euclidean space Rn, and by default we will consider that Rn is a complete metric space. And consider a map S which sends D into itself. Then the Lipschitz constant of S is defined by this ratio. We say that the map S is Lipschitz if this ratio is bounded or it is less than infinity. And this map is a contraction if the Lipschitz constant is less than 1. Further, it is a similarity if this equality holds for all points in the domain D and some fixed Q. Here, Q is also famously termed as the contraction ratio of the similarity or the similitude. So the definition comes as follows. A finite set of contraction maps S is called the iterated function system or IFS. Let us see a very simple example of iterated function system. Consider a set of maps S1 and S2 where the domain of the domain and the range of the both maps is from a real line to a real line. Take S1 such that S1 of x is equals to x upon 3 and S2 of x is equals to x upon 3 plus 2 by 3. So Union of these two maps, S1 and S2, is the iterated function system which represents a Cantor set. So next, in fractal geometry, self-similar object is exactly or approximately similar to a part of itself. Let us see how self-similar sets are formed. A fundamental property of an iterated function system is that it determines a non-empty set K such that K is the union of Si of K, or K consists of images under the maps Fi. K is called a self-similar set or an attractor with respect to the iterated function system S, or it is also called an invariant set of the Fs. Let us see an example of middle third Cantor set. So we have seen that the first map Si is x by 3 and S2 is x by 3 plus 2 by 3. Then S1 of k and S2 of k are just left and right halves of k. So k is the union of these two copies. And the Cantor set is the attractor of the iterated function system consisting of contractions S1 and S2. The two mappings represent the basic similarities of the Cantor set. Let us see some properties of self-similar sets. Self-similar set is unique and compact, and this was proved by John E. Hutchinson. These self-similar sets have a finite structure, which means that it contains details at arbitrary small scales. Next is K is obtained by a recursive procedure. Now let us understand what does this mean. Let us take an 0, 1 interval and name it by E0. We divide this interval. Now what we do is we delete middle one-third of this interval and name it by E0. We get next intervals 0, 1 by 3 and 2 by 3, 1. Again we delete 1 by middle 1/9 of both two intervals, and then we get another smaller intervals E2, name it by E2, 0, 1 by 9, 2 by 9, 1 by 3, 2 by 3, 1 by 9. So we have 4 intervals. So if we keep on doing this, we will end up getting the intersections of EK, which is our Cantor set. Let me say some few words on this construction. At first, it may look like we have deleted so much of the interval 0, 1 that nothing remains, but in fact, Cantor set is an infinite set, indeed uncountable, because it contains infinitely many numbers in every neighborhood of its point. Also, another interesting fact is that the Lebesgue measure of Cantor set is 0. This is a notation for arbitrary set in a real line. A I1 IP is equals to Si of Sp. Soon I will make you familiar with this notation. So in our case, we will consider the following system of finite similarities. Si is a map which goes from R to R, and we take this system of similarities Qi plus C, and in our case the attractor of the system will always be an 0, 1 interval. Q are the contraction ratios. Since these are contraction ratios, they will always be less than 1 and greater than 0. And these are indices 0, 1 and multi indices ijk from I star. Okay, so till this I have given you a good idea about fractal geometry. What are fractals, what are self-similar sets, what is a iterated function system. So now I will talk about little more complicated concepts and ideas. So we know that K is a self-similar set since it is made up of smaller, similar copies of itself. But please listen carefully that these smaller, similar copies can intersect or they can overlap. It is easier to study the self-similar sets when there are no intersections or when there are no overlaps. When there are no overlaps or there are no intersections of the copies, then we generally say that open set condition is true. An interesting property of self-similar sets like topology, house of measure and dimensions, they depend on the extent to which these small copies overlap. So this was the most celebrated condition that ensured that there is not too much overlap. So this condition is fulfilled if there is an open set O in R such that Si of O are disjoint and they are contained in O. But it looks very appealing and simple, but it is not easy to check since, except for some examples, very simple examples. For this reason, a variety of equivalent conditions have been developed. HCF proved in his paper proved that open set condition is equivalent to alpha dimensional Hausdorff measure, proved that the open set condition is equivalent to the positivity of alpha dimensional Hausdorff measure. This result shows that the algebraic condition developed by Banth and Graft is also equivalent to open set condition. They proved that alpha dimensional Hausdorff measure is positive. This is equivalent to the condition of Banth and Graft. It says that identity does not belong to the closure of N, where this N is far away from the identity. So they considered a subset of a topological group G of all similarities. And on G, the topology of uniform convergence on a bounded set agrees with topology of pointwise convergence. This made OSE a little more handy, but still it was not simple. For example, we consider the similarities F1 Fn of form x by n plus yn where n and y I are in integers, still the open set condition does not. So we saw an example when the open set condition does not help us to calculate the Hausdorff measure and the dimension of a self-similar set. So that was the reason a separation condition which is weaker than the open set condition still holds good enough results was developed. A natural way to a condition that is less restrictive than the open set condition is as follows. The open set condition holds if and only if the identity is not an accumulation point of the set of neighborhoods. This term was actually adopted from Lau and Nagy, who gave a definition which is very different, but it turns out to be a similar definition to the definition which I have used. At first glance, if you look, it looks like a minor generalization of open set condition, but it in fact increases the class of self-similar sets considerably. Also, the example which we saw in the case of open set condition, in that example, the weak separation condition is fulfilled for any choice of n and yi's with n greater than or equals to 0. So for the investigation of weak separation condition, there are some number of notations which I have used and I will explain those notations. So first we take F as, as the set of the topological group of all similarities on R, and I star donates the set of finite words or set of finite uh, indices, which are the multi-indices in our case. And we can restrict the set of indices with I. We restrict the contraction ratio using a constant A. So we come up to a definition of a weak separation condition that given an IFS with K with and 0 1 with ourselves with 0 1 interval, it satisfies weak separation property if it carries the property that there is a constant sigma greater than 0, such that for any a greater than 0 and x either 0 or 1, uh, uh, either the copies coincides or there is some distance between the copies, that is sigma and a, where Si and Sj are the compositions of similarities with contraction ratio approximately equals to A. Please note that this holds even without assumption that R self-similar set is an attractor. Next is a finite type condition. For any A, an arbitrary set A in R, let this be the collection of set of neighborhoods from the group of similarities on Rn. So we say that IFS satisfies finite type condition if NS is finite for some A. This means that we have finite number of neighborhoods. And further, I will give an example in which uh, weak separation condition holds. Also, there are finite number of neighborhoods. Next, we go to the definition of net interval. So for each integer a, let H1 HMA is the collection of elements of a set Si of 0 and Si of 1 in the increasing order. So this is actually just a collection of smaller intervals inside the 0, 1 interval. So we name these small intervals as an element of Fa, and we call them as a net interval of level A. And we take the union of all that intervals and write it as F. So for any of the member of F, we donate Ti be the unique contraction with a positive contraction ratio such that the T sends a 0 1 interval to a member of net interval. Also the Lebesgue, also the normalized length is donated by Q, and D is the left endpoint of the I. Neighborhood sets, we say that Si generates a neighborhood T. Va of I is the neighborhood of sets, is the neighborhood set. The similarity Tx equals to Qx plus D is the neighborhood of I if there is some I in our set of indices such that every interval is a subset of an image, and T is equals to Ti of composition with Si. I mentioned you about an example, so let us see an example in which there are finite number of neighborhoods. The examples is a Sierpinski's triangle. It has two neighborhoods at each vertex. In general, the number of neighborhoods depend on the structure of a self-similar set. So in Sierpinski's gasket or in Sierpinski's triangle, there are six number of neighborhoods. So this is a result overview, pictorial representation of the result. So if K is R, if 0, 1 interval is the attractor and the weak separation condition holds, if and only if finite type condition is true. This is also true other way around, and I have used three lemmas to prove that weak separation condition holds if and only if finite type condition is holds. And I have used another theorem to prove the inverse of this equality. So now I will just state the results and show you the how I have done the proofs. So this is the first theorem. It says that IFS satisfies weak separation condition if and only if the cardinality of neighborhood sets of I is finite. That is, we have finite number of neighborhood sets. And here is the proof. Next theorem it says that if S obeys finite type condition, then there exists some C greater than 0 such that for any A less than 1 and multi-index I and J, then either the two copies or 2 points coincide or they are differentiated from each other by some factor C multiplied by A. And here is the sketch of the proof. Next, I use three lemmas for the other side of the proof. The first lemma says that let K be the 0, 1 interval. For arbitrary delta greater than 0, there exists a lambda depending upon delta such that with A greater than 0 and considering the same multi-indices, there is some unique multi-index S with such that the contraction ratio will always be greater than the lambda which depends on delta and it will always be positive. And because of this, that image will be contained in the intersection of two images. Lemma, next lemma. If K satisfies weak separation condition, then the neighborhood is also an element of n delta. This is always true. Next lemma is that S has finite Marine number of neighborhoods if and only if n is finite. And the last lemma is n s of 0, 1 is finite. So let us come to the main theorem, which is the main result of my work and my paper. Let K be the 0, 1 interval, be a self-similar set associated with a system of contraction maps S, such that the weak separation property holds. Then the finite neighborhood condition is satisfied for S. So this is the main result of my work, and I would like to point out that I have already sent this paper to the European Mathematical Society, to the journal of to the Fractal Geometry Journal, and that paper is under review.
Thank you very much.
Thank you for your attention, and if anyone of among you is interested to uh, get some more presentations or some study materials about fractals, I will be happy to provide you. Thank you very much for your attention.
Thank you very much, colleague.